Our next speaker, one of the best kept secrets at ACI. There is an entire staff of engineers working at headquarters, and their job is to help you. And so to help make that introduction of some of the tools that they have created to help you and to help you make it more accessible, reduce some of the barriers, I want to introduce Matt Senecal, who's going to share with us today.
All right, everybody. So, looks like we got a few students out there. What about young professionals? I'm only going to pick on the young professionals for a second. How many do we have out there? Please raise your hand. All right, how many years have you been out? Out of college? Yeah, I know, it's terrible. 3, 2, 5, 2. How was it when you got out? Was it a pretty easy transition? Yeah? Yeah? Did they put you right into doing a building right away? No? Well, they did to me when I got out. It was sink or swim. And so that was one thing when I came to ACI that I came into the industry out of the late 80s and early 90s when computers were really hitting the scene and thousands of structural engineers were being laid off because computers could do the work and the construction industry took a tank. So it was very hard to get a job. There wasn't on-the-job training. You had to basically jump in and do it. And there was a lot of animosity. I was competing against people with 15 years of experience. It was a very difficult environment. So I was always out there saying, you know, there was nothing out there that ever told me how to design a building. I went to school. I went to some pretty decent schools. And they did a great job teaching me the basics. I know theory inside and out. You know, thank you very much. But as far as when I got out into the world and they said, here's the architect's drawings, you got a week. Okay, now I went and worked for a small firm right off, and so we did things like little Texaco gas stations, strip malls, churches, things like that, which I have found actually to be more challenging than a 16-story building. You go out and build a 10-foot tall masonry fence. You have some steel supports coming out of the top of the masonry, and you put a timber beam on top of it, and all of a sudden I'm like, timber beam, a steel, and I'm attaching this to that, and where's the code out there that tells me how to do that? They don't exist, or they're coming along now though. So it was very challenging when I was a young professional from a student going out to the real world. So when I got to ACI, we showed, you know, we've always been thinking about young professional students and that transition that you have to do. All right, so back in 2005, we started a series called Code Cases, lack of a better term, where we went out and asked 4 different professionals out there and said, can you just give me a design that you've done recently and talk a young professional through your design? And we found a handful of people to do that, and they were quite gracious. And the company was quite gracious to give up their drawings, the calculations. You know, it's a little scary to give that out to some place like ACI, right? Because we're going to share it with a lot of people, and you're going to get a lot of scrutiny. So thankfully, you know, we had a lot of people review it, and we kind of sanitize things because, you know, we all do engineering tricks that make the world go faster. Some of them are safe, some are a little questionable. But that's the whole thing of experience, is it not? It's know when to use your tricks and when not to use your tricks. So we kind of cleaned up things just a little bit for y'all. But this is one of those things. And one thing we use as a tool is we use this thing called RoboHelp. And I don't know if you guys remember 90s. In the 90s, if you turned on if you got on the computer, if you downloaded a program and you click the help button, what would you get? You'd get a little book that popped up. And that little book would have all the help in it. You didn't have help off the internet. You had this little pamphlet that would pop up, and it was RoboHelp. It was a very early product, and that's what we made this product in. It's an HTML editor, and it produces what you see right here. A nice little help guide you can see right here that we have. All right, so here we go. So you can see we have a nice little menu here, just like we would have in any book that you might have in this, and we can see all these different titles in here, and they can collapse and they can open up, and we can start right here at the top. So this is a nice HTML page. This program runs on any web browser that you have out there. I have, as a handout today, about 40 of these USBs that have that on that. There's like one folder that contains something like 1,400 files, and you click on one file and it starts the whole thing. I also have another file on there which is it's called a compressed or compiled HTML, which is only like, it's a little less than a meg, but it'll only run on Windows. So I mean for you guys to take this, you guys can copy it, you can have it. We'll figure out how we can better dispense it. This is all I could get across the border without raising any more eyebrows than I really wanted to have raised. Okay, so
Emails of those that don't walk away with one.
that'd be great. So I'm here to introduce you to this tool. I'm not going to go through the X's and O's of design. That's all in here. So I just want to show it to you so that you can go home and then at your own leisure you can say, I kind of wonder how this person went about it. So here we start off. We went to Klein and Hoffman, a company that's out of Chicago, which you might have heard, and they built this beautiful 16-story hotel in the areas around Chicago, and it had some unique attributes to it. The first floor was 28 feet, and then before it went off to its normal 10 to 11 foot stories thereafter. It was a flat plate, but the column spacing was highly irregular. So you had 48-foot spans next to 26-foot spans, and then they made a little diamond pattern out of the columns. All right? So that when you want to go to a normal flat plate design, and you're going to go, I'm going to go use the direct design method, and all of a sudden you start going through the criteria for direct design, you're like, well, no, I can't use that. So, this is a real life problem, and this is how they approached this problem. Another interesting thing is I can show you in a little bit here, is this ends up being an extremely stiff building. So if you go back before you had 3D design and using finite elements, and I would use a classic 2D frame with a stiffness matrix, I would calculate deflections on the frames on this, and maybe I'd get an inch or two deflection at the top of the structure. Used a finite element analysis program for this, and it had 0.1 inch deflections at the top of it, which kind of makes you go, I wonder if it really worked, right? Because, a building does have to deflect to get your stresses, right? But when you take a closer look at this structure, it's like a perforated pipe stub sticking out of the ground. It has so much concrete with just a little few holes around it. So it is indeed a stiff structure. They didn't really have to worry too much. So some of the nice things about this program is, okay, so here's Klein and Hoffman, and to give them a little, advertisement, you can click on these things and it'll take you to the website and you can go visit. We come down through here. Here you'll see it's a kind of a classic. Your design is on the left-hand side, the commentary's on the right. And you go through here and we can see the statistics here of what was a lateral force resisting system in one direction versus the other. It was a shear wall versus a moment frame combined with shear walls. And we did lots of nice links in here too. So like if we're talking about building geometry right off and you wanted to get a good idea of it, it takes you right here to the floor plan. And to kind of make this kind of nice, you got a floor plan, you can click on the plan and then it'll blow up and you can take a look around. So a kind of nice little tool to help you quickly get around, to get a sense of the building as you're going through and visualizing the design, visualizing what's happening with this structure. All right, and then we just click our little back arrows as we do, and on we go. So we have a description. Architects come to us and said, here's a building, get going. And so you get going and the first thing you do is design a beam, right? Because that's what we learned. We know how to design beams. Well, not really, right? So if the first thing you learn, one thing you hardly ever learn, is that you have to go talk to your building code official, right? First thing you do, at least in my day, was you called up the local building code official and say, what code do you go by? Or do you have any special requirements? Especially Chicago. I don't know if it's still true. The myth is that downtown Chicago still goes off the 83? Something like that, yeah. So, and then they have a lot of extra, other little requirements on the sides, and of course they'll let you do other things if you can prove it. I think the last time I dealt with Chicago, we were building a Sprint battery house, okay, which is a 2-story structure, just 300 PSF floor loads, and it was flat plate, and we decided to use a computer model, and we sent it into Chicago, and the person says, prove it. Prove that your computer model works. And we had already spent all our money on the design, and now we have to, I want to see it by hand calculations, and so that took us a while. So it's good to talk to a local building code official to understand what you're getting into, to understand, am I going to use, is it the IBC that we're under right now? Is it something different? Is it something older? Have they modified that? I think in Indiana, the last time I'd worked in Indiana, they had chosen all of the natural loads for every county in the state. So you don't choose the snow load off of a map. They'll tell you what the snow load is. So it's very important to talk to your local building code official. And then you get out into the world, and all of a sudden you realize there's all these other documents that no one told you about. ASCE 7, okay, that's the loads code. You can kind of see down here we have links to those types of things to kind of help you go there if you haven't heard it. So here's ASCE 7 and a little advertisement. You can go off and you can get ASCE 7 where it is, or peruse around in there. So we have like a lot of nice little links in here. So you start with that building code official. You get the different codes assembled that you need to think about, and you start piecing them together. All right. So, occupancy, we might have to look at the building code along with ASCE 7 to help understand how we start determining our loads. And so that's what this commentary is that engineer who went through this process had to think about these things. And they're saying, I'm going to grab this value here, I'm going to grab that value there. This is maybe why I did what I did. We'll also talk a little bit of things about like fire ratings. Sometimes people get a little confused about that. ACI 318 doesn't have fire loading in it, right? Or fire design in it. So you really need to go to IBC. They kind of control it. The weird thing about IBC is that you can use the IBC all by itself, but it also points you then back to ACI 216. Why 318 just doesn't point you to 216, I don't know. But that's a long political issue that I can't get through. So anyways, but that's one thing you have to think about. The architect, by those occupancy ratings, has to come up with a fire rating. For this particular structure, a 2-hour fire rating is what was necessary. Well, inherently in ACI 318, you get about a 2-hour rating. Those are things that you don't learn, right? You kind of explore those things on your own and learn those types of things. But it's good to kind of crack 216 every once in a while and kind of see what cover gets you, right? So you get a feel for what just a natural design will give you when you go out there to approach a structure. Once again, that's what this whole process was about. I don't get into too much project specifications in these. That's almost another whole, I could have had another 100 slides in this to get through job specifications, but it does help you along with drawing notes. I said earlier, when I got started out there, I worked for the really small firms, right? These really small buildings. I never wrote a set of project specifications until I went to another firm and started doing larger structures. Everything was notes on drawings, and that was just fine for small structures. And it works. It works really well. ACI 301, which is the concrete specification that we have here, is a reference spec. It's very simple to write a concrete spec on a set of drawing notes. if you use the mandatory checklists in the back of that document. Basically, most set of notes that you'll see on a drawing, let's see here if I have a little link here to drawings here. I'll just go on down here to general notes. Here's a notes sheet. We got some general notes. Or let's see here, we got concrete notes. Let me go back one. Got concrete notes. You see these little notes you put on drawings? How did they get those notes? Where did those come from? Why are these so special? And why aren't they just in a set of project specifications? Most places I ever worked, someone in the office was designated the concrete person, and they found that magic thing called ACI 301. They learned about a thing called checklists that were in the back of that reference specification, and they started answering those questions in the back of the document. And as they answered those questions, they wrote them on the notes. Okay? And that's pretty much how most people arrive at the notes on job drawing or on drawings that you put out there. And then you'll have an architect that comes along and says, I need a set of project specs. Would you do the material specs for me, please? And then in which case that would be another seminar that you need to go to. So, okay. Another thing you collect is geotechnical data. You need some of that information in order to complete your loads, to understand your analysis that you're going to accomplish, right? So we have a little section on that. We get into loads and effects, the load combinations, patterns. You'll start to see as we get to this point in the project, I start to put in little links or little drop downs to ACI 318.14. 19's not out. I updated this from 318.05 to 14 because that was the last time I worked with this. So the structure was actually built under 318.05, but many of the requirements are the same, and I did update them, all except for wind. I had too many graphics in there that had to do with wind design, the numbers and stuff. But what's interesting about wind? Young professionals, what happened between ACI 705 and ACI 710? Can anyone tell me? Yeah, ultimate load, right? Right, so we went from a 1.6 times the wind load to a 1.0 times the wind load. You know what the difference is? 1.6. There's no mystery. They didn't reformulate everything. They did provide a bit more information on lots of other things, other structures and things like that. They did do a lot of improvements, but the basic wind design is 1.6. So if you saw a service load design from the early 2000s, just multiply it times 1.6, and now you're an ultimate load, and you're good to go, all right? The short version of many long wind things you'll go to. So anyways, we talk about that in here, load combinations, patterns, how do you move your live loads around, alternating live loads, that kind of concept, two spans together, every other span, checkered span, on floors, checkered, alternating live loads, that stuff is in here with a little information. You can pop down and read it, or you can just have your 318 open and you can read along and kind of see the full picture instead of just the individual requirements. And we just put in here things, the dead loads, lateral loads in here you can see. So here's like a wind load diagram. You can get a sense of how these things were calculated as we move through here. Deflection limits, if you look down here, this is where gravity lateral deflection limits. You see here, the maximum calculated drift due to seismic forces in the north-south direction is 0.1 inches. When I got that from the structural engineer who did this, I go, you gotta be kidding me. 0.1 inches, I just never seen that before in my life. And he goes, no, it's okay, it really is okay. And then that got me to thinking, a lot of these code requirements, and I'm just kind of putting a little fear into you, is we had a lot of fluff in a lot of our equations because we are designing by hand out there not too long ago, or with very simple first order analysis matrix type designs. And so when we were assembling the process in which we go to do design, we're basing that on these more simplistic methods of analysis. Okay, so we had some wiggle room when we designed a frame in one way, then a frame in another way, right? We didn't have the full 3D effect. But you know, as time has gone along and we get more and more dependent on computers and we get closer and closer to actual values on the column, it used to be that I could look at a frame in one direction here, and I look at a frame in here, and I'm done. But now we're putting, you know, we do a 3D analysis and we got this corner column. I get nervous sometimes with the way we design that we're cutting it a little too close on maybe our corner column designs. We got to really think about, you know, how close we're getting to actual loads and the actual values that we have in the equations that are in ACI 318. Just a little something to think about, because really, I think my structure is going to deflect more than 0.1 inches. So something's happening here in our assumptions that we need to somehow feel good about in our mind. You should answer that question before you move forward. Okay, I already talked about drawing notes in here, and then they talk about structural analysis. So structural analysis, we start off with member sizing. A lot of really nice things. We have this new thing called Chapter 6 in ACI 318.14. You know, the old 318, wonderful code, and if you grew up with that code, you're golden. But if you were approaching that code as a young engineer, it was really hard to kind of jump right in and start design, and that's why we reorganized it. And one thing we found was we had a lot of cool analysis techniques that you were permitted to do by hand, right? Because this code is over 100 years old. It assumed in the beginning that you were designing by hand, and so it had some simplified methods in it. And although we might not use those much anymore, they are good for helping us come up with some member sizing or to check our complicated analysis. So 318 has decided to keep a lot of those simplified methods in, and it's in Chapter 6, to kind of give you a feel, right? So you're getting a computer analysis, you can go into Chapter 6 and you can look at these simplified, you know, techniques, and you can kind of check yourself a little bit. Say, am I in the ballpark? Am I within 25, 50% of maybe a complicated model, and it makes you feel pretty good. If I'm off by an order of magnitude, I shouldn't be off that much even with a simplified method, should I? So, I mean, you know, these are questions you got to ask as a person entering the world of bigger design. But anyways, there's a section in here. It kind of helps. We also have a lot of tables and all the members that help you arise at a certain thickness to start with. A lot of times, and in the case of this particular structure, the size of the member, or at least the initial size of the member, was dictated by the architect. That's going to happen to you a lot. This 12-inch by 12-inch column going up 30 feet is going to look beautiful, right? So a lot of it is, you know, over time you're going to get a feel for what is basic. You know, what is normal? When am I getting in trouble? I really enjoyed very much, the funnest time in my life was doing the small structures. Why? I would go down to Denny's with the architect and get the Grand Slam breakfast, and we'd go over the design, right? It was awesome. I really loved that, you know, versus, you know, we're all stuffy and sitting around a table and everyone's already got it all figured out, and you know, you get to sell your structural design, right? You get comfortable with your tools. And, but anyways, you'll get a feel for concrete over time. It doesn't take too long. It just seems so scary at first. I don't know why that is. Maybe because the way the code was written before, you had all this theory in your mind, and you had to have it all up there, and then you had to apply it. And I could apply it to any section in the world I wanted to. Well, that's not how it really is. Right? You know, realistically, we're talking about a handful of sections that you normally use for a column or a beam, and those are your go-to section sizes, right? We're not changing every beam size. We're not changing every column size. We got formwork economics we got to consider. It's getting better and better, though, by the way. Those forms are getting more adjustable, reusable forms. These are all things you start to pick up over time, and hopefully the more experienced engineers in in the offices are help guiding you along. But this page right here talks about initial member sizing. Because we need initial member sizing to run our analysis. We need to put some sizes in our computer program. How do I arrive at those? That's right here. They used a finite element analysis for this, and finite element analysis is addressed in 318.14. They put a little section in there and they said, yes, finite element is good for everything. It's good for first order analysis, second order analysis, nonlinear elastic analysis. But at least they're starting to talk about it. And what I hope over time is they start to provide us a little bit more guidance and code, especially when it comes to things like flat plates, when we're collecting a lot of forces across a strip, and we have these somehow we're getting super high stress concentrations, particularly at our columns or something like that. How do I normalize that? What happens if the stresses just seem oddly high? How can I mitigate that? How can I feel comfortable that what I'm looking at makes sense? That I can just normalize, just add up all those moments and divide and get an average value. How can I do that? So hopefully, we'll get a little more direction in our guides and then a little more direction in the code going forward. But at least we're now even saying that it exists, which has existed for a very long time. We go along, and I was talking about evaluation of result, or I was talking about using Chapter 6 to evaluate your computer program. We have a whole section here called Valuation of Results that does just that. So here we have this very odd floor plan, very long spans, very short spans, flat plate, columns in a diamond pattern. And let's see here if I can show this quickly. So in here, the computer program gave us 170 kit feet. And then I just use the direct design method. I just ignore the fact that I don't meet the requirements of it. So it may not give me a safe design, but it should let me know whether or not my computer analysis is making sense. I might be just outside the values that I'd normally get. I wouldn't use them for design, but I should be close to the values. And you can see as you come down here, come up with 148 kit feet. So 148 from my hand calc versus 170 from the computer. So I can say with some reasonableness that this odd thing that I am looking at with an FEM analysis is giving me something in the realm of possibility. Right? So we have tools out there. These old tools are there for us, and they're in the code. And you don't have to go that far to go and find them. So then in here, after we get through all this upfront stuff, and I spent a lot of time on all this upfront stuff because that's the stuff you don't learn in school, typically. There's some of you out there that are doing all this, and I applaud you because you're preparing your students well if that's what they're wanting to do, right? But we're all wanting to do different things. This is specifically to get you in the world of building design. So from here, we have member designs. We've got the flat slab design, the spandrel beams, interior column, the shear wall design. For whatever reason, everyone seems to have a problem with designing walls. Not really sure why. I guess maybe because we just don't talk about it enough. But that seems to be, even when I go to general practitioners, how do you design that wall? They get very defensive. Oh, okay, all right. So it's one of those funny things. So we have examples in here how to design the shear wall, and we got the mat foundation as well. So all of these are in here, and they follow a general format. Let's see here, we got the flat slab. We usually start out with flexural design, and so let's go ahead and pop into here, and we just kind of go through. Now, I don't take you through every calc unless it's an unusual calc, just because you can go to your textbook to get, the equation for, designing a square beam, or a square section in a flat slab. So a lot of times we just give you the AS and, that would be required, and kind of take you then down through the rest of the code and take out those extra principles to fill in all those little gaps that you might not have read about or learned about. But once again, that individual who designed this is taking you through their thought process as they design the positive moment reinforcement. In this case, what a lot of people don't realize is, you like in a flat slab, you have the negative moment reinforcement, the positive moment reinforcement, and then we got this thing called the unbalanced moment. There's a little bit of moment right around that column, whereas it goes into the column as moment, but as it flows around the sides of the column, it transfers on shear, right along the sides, like a spring. Think of a spring coming out the sides, right? So they've come up with some equations that says we need to concentrate on that little portion of the moment, and we need to put some of that, make sure that we had enough of the steel for our general strip design, that enough of it is right here around the column, and then we got to make sure part that's transferred in shear is accounted for in shear. And I think this example does a good job stepping you through that, showing what we mean in ways that maybe you might not have seen before. Other little things I want to show you in here is we also have references in here. So if we saw a particularly good paper that really talks about that, we have a link to it. As students, I think you get to most of these papers for free, I believe. I think you get to the structural journal, materials journal, and all those kind of things as students. So you can read these papers, and we selected these papers because they were good practical papers, not because they were highly theoretical. So anyways, we come back, so we have a little extra things like that in here that are nice and helpful, and then we go through the detailing, trying to understand how you go about the general thinking of a section and how you would detail it, and a little bit on plan, and then finally you can go to the actual sheet and see how then, we saw this in the beginning, how you would call it out on the actual drawing. So how you might conceptualize the detailing as you're going along, and then how you might actually present it on a set of drawings. And so that's all provided for you in here. Let's go back to the Spandrel Beam. The reason why we chose the Spandrel Beam is because it has torsion. Wanted to take you through a little bit of torsion, how that actually plays out in a real life design, and how it, as you kept in this case, you can't ignore torsion. There's a thing called threshold torsion. If you're below it, you can ignore it. You can't ignore it in this case. So we were trying to find buildings that pushed you a little bit, right? Problems is like, oh, I was hoping it went away. It didn't go away, right? And so now we have to do it. And this, how did that individual tackle that problem? Right? And so then you got transverse, longitudinal detailing. You start to see a pattern there, right? Interior column, pretty simple stuff here. I mean, columns are, we just use our interaction diagrams. I think one thing that, and it is said in here is, once I usually pick a size largely dictated by the architect for columns. And they're usually these days pretty good, I think, at picking an initial size. You might have to adjust it slightly, but you usually start at about 1% steel, the minimum, right? That's where we like to start, and then we go up from there, and just once you start getting past 2%, and that's kind of discussed in here, you might want to start rethinking about how that column is designed. So that thought process is in this overall case study. Shear walls. Once again, shear walls aren't really all that complicated. I think, once you put in the minimum horizontal and vertical steel, basically you're checking it as a column. There's the magic trick to it. But also realize walls are generally lightly loaded for compression. All right? So you generally don't have to have confinement steel. Now, if we're talking about a large shear wall in plane bending, right, we're going to have possibly, boundary elements on the outside, and we're designing those elements as columns. But for most shear walls out there, it's a pretty straightforward design. We put in our minimum vertical and horizontal. We do a quick check on the combined stresses as a column, and we're done. And for this particular structure, that's true, and they kind of take you through that thought process. And the mat foundation, You know, here, how is the mat foundation? It's actually talked about earlier in sizing. You know, it's really easy to pour a lot of concrete in the ground, right? And typically you don't need a form. So we're not really wanting to put any shear reinforcement to a mat foundation, and that's pretty much what you come about learning about mat foundations. You make them thicker and thicker and thicker until all I have to do is put in top and bottom reinforcement, and you put in the minimum reinforcement. It's 5 foot thick, and you're putting in number 9s at 6 inches. So, you know, there is a little economics you have to think about before you just rush off and make that foundation as thick as possible. But anyways, so I have an example in there. And then just as for fun, you know, some people are always confused about how do I approach like a stair design. So we threw one of those in there just to kind of, you know, this is how I would do it kind of thing, because you're just not going to find it very many places. Column to footing details, there's a little bit more that's in the code, so this was kind of to make you aware there's extra code requirements for certain types of connections. And then we ended up doing a little left splices and embedments. So most firms you're doing all this design, and you're showing your floors, and maybe you're putting your reinforcement in the floors and you're showing it, and then you got all these schedules that you have for your beams, for your columns, for your walls. And then you have this general sheet, which is a general details, small walls. And one thing that 318 says is you have to state where all your splices are and the length of those splices. And if you're going to do that for every set of drawings, I mean, you'd never get done drawing. So most of us out there end up making some sort of splice and embedment length table, right? There's all sorts of them out there. CRSI has a handful of different ones, but we kind of took you through how you might go about building one of those tables, okay? So just a bunch of little bells and whistles out there, you know, why this, why that, where does that come from, how do I calculate that? And then I've been kind of showing you as we get along in here, we have then the drawings down through here, and this is one of the first ones we did, so we decided to have these as pop-outs, that you could do this. On here, in one other folder, we actually have the full-size PDFs in there, so if you have a full-size printer, you can open up that file, and you can print them out if you want to, if that floats your boat. But anyways, you know, shear wall details, what do we, you know, door opening, you know, typical reinforcement around an opening, the wall schedule, what is a wall schedule, how did they put theirs together? You know, kind of gives you a feel for how to put together a set of drawings. And with a couple clicks, kind of jumps right around and all that kind of stuff. So that's the gist of it. I think I'm just going to stop there, if that's all right. And I'd like to answer questions or just talk about situations of getting out there as any concerns you have as a student, any problems you might have gone out there as a young professional. Was it as scary? I mean, for me, it was really sink or swim. I mean, I was really surprised. The first job I got was a masonry structure. And we never even talked about masonry in school. And they gave me the code and said, I'll give you 3 days to learn the code and 2 days to design the building. And they said, and we've given you 4 days too many. and I was like, it was literally a sweatshop. They didn't have an air conditioner. One day I went in and worked in my t-shirt and I was sweating on the drawings. But I loved the place. I really did. I really enjoyed that. All that, I really enjoyed it. I don't know. Any of you guys got a story you want to share? I mean, this is young professionals, isn't it? Students? Yes, sir.
Fun fact, Chicago still asks for all the calculations by hand.
They still ask.
My foundation, caissons, settlements, slope stability, they're all done by hand. And if you submit it in an electronic file, brace yourself. It's coming back. Pressure meters, you have to do it by hand. So, yeah, the same code.
So when you're out there, make sure you know what you're dealing with, right? I mean, we were a young firm that would take any place, anywhere, and we took a Chicago job not knowing what Chicago was going to do to us.
One important thing that I learned, I work for flood testing in Chicago. We do material testing and structural analysis and stuff. And it's like, know your testing requirements as a young professional. Everybody else in the nation, you have to do a pile, you test it to 100% of the load. In Chicago, you have to do 200% of the load, maximum load, sustained for 48 hours.
Really?
Yeah. So that doubles the cost or triples the cost of your foundation testing and design. So when you're going to a job, I found that out the hard way. But when you're going and accept a bid for a job, make sure you know the requirements for the testing. Some bridges, they ask for concrete testing every truck. That's, yeah. That's what about later, but know your requirements of testing.
That's right. That's right. Yes, sir.
So as an old professional, I have a little bit of a suggestion to young people. Significant digits, don't give 9 significant digits to
So he said significant digits, lose them, right?
I was going to ask about what you have up there. Does that go through, like when I've done my design, it's always like a preliminary design where you do top down, get your foundation load, and then go bottom up. Does that go through that sort of stuff, or is it more of like a final design?
This is more of a final result. This columns or this wall schedule is just the end design that was on the. I didn't do a column takeoff as a learning tool in this, just because we don't really do things by hand as much, you know, and the computer analysis anymore. I mean, people are putting in whole models in 2 hours and getting some sense of things, you know. That one thing I did do is we actually remade 4.3.18.14 our design examples. We used to have a committee that gave us it's not design examples, it was a design manual. So when you didn't have computers, you had quick lookups, right? And ACI had one, CRSI had a big book of them where you can just do lookups of different sizes and go in and quickly get a sense of design as you're going along with the loads that you have. I think with all of, you know, you have big, large computer models you can out there, you have lots of little ones like InterCalc is pretty decent, I always thought. I mean, just to have a little design to column, design to beam kind of thing, just to check on the side. That was a little bit more flexible than trying to go in and remember these charts all the time. So we made a design example handbook, SYPACv2. It's well over 1,000 pages, and we do stuff like that. We teach you the portal method, which is you can calculate your lateral loads, the loads in your columns and on your beams. In 15 minutes, I can do a 10-story building with lateral loads. I can get for the lateral loads, I can get all the shears and moments and all my beams and columns for that lateral load using the portal method. Now, it has limitations, but yeah.
And the other thing I was going to say was, I remember as being a young engineer being overwhelmed with trying to make a decision and just getting started. It's not so much the decision, the answer that you come up with, it's that you make a decision. And that it's right or wrong, you could always go back and correct it. But I remember just sitting there for hours just trying to figure out what's the right path. And it doesn't really matter so much. It's really just go in there, make a choice. If it's wrong, it's fine.
Get it done and get it in front of someone. So he's saying, you know, don't dwell on it. I still have that problem with older engineers. I need to get the job out the door. I get paid by the paper or by the electrons, right? The longer it sits on your desk, the worse it is for the company. So if you're really struggling there and then you want to go off and do a research project for a week, remember you're burning hours. So you need to get in front of someone senior to help you along. Don't sit there. It's it's not that you're stupid, right? Just you have limitations. You're young. You don't know the answer. Go and ask questions. Bug the living daylights out of the oldest person in the office until they're just yelling at you to go away. And you know what? They'll love it. They love to yell at you, and they want you to come back. Okay? I mean, I'm serious about it. It's just the way the world works, right? They know that you need to ask the question, and they know that they need to answer it. So get up, get over to it, and ask them the question. Or just finish the darn drawing and get it in front of someone so that someone can say, okay, you did this, this, and this wrong. You're 1 week ahead of where you were. Okay? Yes?
Two questions. One is on the two-way slab. Do you have the contact with the rebar over column? In the past, we use X plus Y. This is in the column street, we have a certain center rebar over column. One is smaller range, one is bigger range. This is called X plus Y.
X plus Y? Yes. So, I mean, people call out, so that's another thing. There's an art out there of how you want to call out your different reinforcement on your drawings. And he just explained the X plus Y. You know, we all do it differently. We just had a new detailing handbook that went out, or the 314 just put out a new, it was not a handbook, but they kind of explain how you might want to communicate for the different members and why that communication might be positive or negative as it reaches the detailer on the other side. X plus Y, I mean, the way I've always done it is, and I'm trying to remember exactly how the X plus Y work, but I always just have uniform reinforcement everywhere and then 3 here, 4 there, yeah, like that, yeah, just, that's the easiest way. Try to find that minimum spacing that you need and a little bit more here and a little bit more there. What you learn about concrete is very forgiving in bending. It's never forgiving in shear. And you got to understand where there's restraint in your structure. That first floor likes to crack on you, right? Because the bottom floor is fixed pretty hard to some foundation. It's adjusting up to something that can move. The stories after that tend to not be too much of an issue. So, you know, sometimes when I was sitting around, I'd watch older engineers. When they got done with their design, they'd just take a big step back from the drawings and they'd look at where things look a little tight. Things might crack, that there's a little bit more restraint. And they'll just go in and go bar, 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 for absolutely no reason whatsoever. Then they know that there's going to be a stress riser there. There's going to be a crack that opens up, and all they want to do is make sure that crack stays tight together.
At diagonal bars.
Diagonal bars, primarily. That's right. Because that's usually happens at corners. Yes, sir.
And another point. My company, when I tell two engineers to keep using, one is all the reference book with the charts. You can use that to check your computer results.
Yes.
Two is when you're stuck for something for half an hour without making progress, it's time to stop. And I don't allow them to spend more than 30 minutes on one thing.
That's good. It's good. You know, we want, either we're stuck because we want to learn, we're afraid to ask a question, I should have known that. Come on, you got an education. It's not a bad education. Sometimes you'll hear some of the older people say, well, you should have learned that and whatever. Ignore them. You know, if that's keeping you from asking questions, you're going to have a really hard time. You just got to get up and ask, and just got to take some of the, I don't think it's as bad as it used to be. I think people are a little more generous with their time and a little less cranky about giving you a hard time for not knowing something. But if they do that, just ignore it. Just move on. Ask them again. I don't know. Tell me, right? Yeah. Yeah. And they'll love you for it. They'll love you for it. So.
I've got a comment about your 1/10 of an inch of deflection.
Yeah.
Okay? We don't build buildings to that degree of precision. The reality is the tolerance on all those 16 floors of columns is nowhere near that. So it sounds to me like this is a computer program that needs to have a reawakening because it's not actually contemplating real-world tolerances.
You know, it's one thing that always has bothered me is when I learned finite element analysis in my first school, we didn't learn how to put it all. We had to build the node, right, to actually understand how that information is being transferred from node to node. And what you start to learn really quick is you can change the stiffness of the calculation, or the end result of your calculations quite quickly by the types of shapes you choose. Now, what's funny is that all of our computer programs out there seem to have settled in on a certain shape. And if I remember right, I don't remember there being such a clear answer on the right shape to use. And so I've never enjoyed FEM analysis. I mean, to be honest, I stopped designing, professionally to any great degree 10 years ago. So, I mean, that's where my experience ended on today's computers and stuff. And the last time I did a 3D analysis, I always double checked it with a 2D analysis. That shows my age, I guess. But I felt so much more comfortable with the values I was getting. You have rules of thumb and I think the wind committee's trying to figure this out, is what is an acceptable deflection limit for wind, right? They're trying to pull together, they've already polled a bunch of firms to come up with a value, and I don't know if they're going to put a tech note together, and I don't know if they fixed it, but like this company, and they put it in this case study, they use H over 500. Are we even H over 500? This should have been, I did do this for giggles on this 20 years ago. I did a hand calculation and I came up with 1.4 inches. And that made me feel a little bit better. Right.
In reality, with 16 stories, depending on how it worked, you can get pretty close to a 1/4 inch in tolerance from one story to the next.
Absolutely. Oh, absolutely.
And so this program is not allowing for the real world at all. So we're dreaming that we understand how the structures behave.
Yeah.
Because we don't.
Yeah.
It's just nonsensical. And I don't think it's a very good idea, basically. And I learned finite elements 20 years before you did. We were designing the elements.
Yeah.
Right? So,
Yeah.
and that's what I did my graduate stuff in. But, come on.
Yeah. I wish I could have, these people probably, I don't know if they even had the ability with a computer program they get to choose a different shape. It used to be you could choose shapes in FEMs. I don't know if you can. Yeah. There was okay.
But yeah, that's what we did in the old days.
Yeah.
Nowadays, you gotta have a canned program.
Yeah.
We actually understands how it works.
Yeah, one of my comments is that if you look into the code, there's all these different equations. It can be overwhelming. And if you go back to basic mechanics and all the stuff you learned in school, in those equations, it's a part of what you learned in college.
Yeah.
And you should be able to kind of sort of diagnose it. Okay, this is why it's this kind of value. But you have to rely upon the stuff you learned in school. So that the equations are there. You just have to kind of decode them a little bit.
Yeah. It's, so, saying the basics are good. You're not going to learn it all overnight. But, just you run a model, check your reactions, check the deflection. The first thing I've always done when I'd run a model, I check my reactions, check my deflections. Because that right there would tell me whether or not this model is behaving at all the way I thought it was going to behave. And I'm not looking at anything internal to the surface. I'm just talking boundary conditions. Because I've designed way too many buildings where at the end of the day, the person, I handed off the drawings quickly, and he goes, you got a 1-story building deflecting 5 feet. The reactions were okay. One of those things. So, I mean, it's those little things that'll tell you whether or not, you got all your releases right in your model, and it's just the general boundary conditions is just a great place to start. And you just keep moving through the structure, and it really doesn't take long before you really start to master the basics. But it will take a couple of years.
The other component piece of that is to get out to the site as much as you can.
Oh, that's wonderful to see
How it
things.
actually goes together. And
Yeah, and it'll scare you a little bit. Yeah, yeah. You know,
I think one of the things that amazed me is on this point is like something that would take weeks in my office to design takes them less than a day to build, and something that took me less to a day to put on a piece of plan takes them weeks to monitor out in the field. So it gives you a completely different perspective to see both of those worlds.
absolutely. Just to kind of get out there to see all the rebar laid out and to see, you know, how much they bend that rebar around things, and kind of makes you go, hey, are they allowed to do that? You know, that kind of thing, and just kind of ask those questions. And, you know, it's good to see those things and then ask. And you'll find sometimes a lot of people don't know all the answers. And it's okay, right? So, you know, we all say, well, I don't know, but it always works if I do it this way. You've never been in trouble. Well, maybe we should try to figure that one out. But yeah, I think we're okay. I mean, there's a lot of that in the design world, right? Because I've been stunned as the staff member here, and I've been over 15 years now, and I hear the academics talk, and they say, well, the design engineer knows what to do. And then design engineers over here counting on the academic to have formulated all the right equations and everything and know exactly what to do. Both sides are assuming the other one is smarter, and it's like, okay, there's a disconnect here somehow. It's an interesting, it's amazing that it all works, but it does all start to come together at some point. That's the one thing I gotta say is, once you're over the hump of learning concrete, I think it's by far the easiest material to design with. That's my personal opinion. And I started with, my second job was Butler Manufacturing. If you don't know what that is, that's a metal building manufacturer. Okay, so I've done little buildings of all sorts of things where I put, you know, a metal stud, first floor, wood floor on top of that with another wood floor on top. So I'm trying to screw through a wood floor into and I'm trying to find the capacities of these things. There's no capacities out there. I go to the manufacturer to find the shear on the particular configuration, and I'm like, I wonder what factor of safety is on that. You know, there isn't one. Who knows? You just get into all sorts of wild situations out there as a structural engineer. I found that immensely fun. So I hope you do too.
Questions?
I was just wondering if there's another way to access the information. Is it online as well? It used to be online, I believe.
It used to be online. You know, the web has changed so much, and we had stopped maintaining it. And so what I wanted, so it's here. I want to make it available. I'm not trying to hold on to this at all. If you guys know each other, take one and copy it from one to another. If you can find a different way of communicating it to people, that'd be great. If you just want to give your email or something.
Can you send it by email? Like our company, we can't put one of those in our computer. Our security's so tight.
If we put it where you can go get it, can you go get it?
Potentially, yes.
Okay, that's,
I'd be fine, yeah, like with a Dropbox
Make sure
or
I get
a Google Drive or something like that. It's nice because the compiled HTML is less than a meg. It's beautiful. It's like 14K. And it has all this stuff in it, but yet you can't send it through Outlook. It's a banned format. I swear it's safe. But I, you know, because I've been wanting to send and communicate these things, but I can't send, you know, 1,400 files, 40 megs just becomes kind of crazy. So.
all right, fantastic.
Okay.
Let's thank Matt.